Hello and good day everyone. My name is Ratna Fatinah binti Muhammad Basri, metric number 194408. So today I will present my final year project, Design and Development of Portable Biogas Digester for Domestic Use. Some introduction for this study. So first, what is biogas digester? Biogas digester is a closed vessel where anaerobic digestion took place by consuming organic waste to produce biogas and having a byproduct of slurry. According to Nevzorova and Kucherov 2019, says that despite numerous studies on portable biogas digester, the potential of biogas energy has not been employed fully in most developing countries where domestic waste is poorly managed. So in this study, a comparative review on available design type of portable biogas digester were conducted to determine the suitable digester design type to be fabricated and modified to meet the domestic requirement. For the problem statement of this study, so first, domestic waste disposal through landfill and incineration are no longer acceptable as the method was uncontrolled and emit more toxin to the environment. Second, most of the available commercial portable biogas digester for domestic use is expensive. And third, the biogas digester are usually bulky or bigger in size. Moving on to the objective of this study. So first, the main objective is to design and develop a portable biogas digester that produces biogas from various types of organic waste for domestic use. In order to achieve the main objective of this study, there are several sub-objectives that are required. First is to study and select the suitable portable biogas digester design type for domestic use. Second, to fabricate a modified design of portable biogas digester that was selected to meet the desired design specification for domestic use. Third, to determine the biogas production of the developed portable biogas digester. The first methodology is design selection, where selection matrix method was used. Table 1 shows the filtering table used to evaluate the available design concept of portable biogas digester. The evaluation will be based on the selection criteria for biogas digester for domestic use. On the left is the filtering table scoring procedure. Second methodology is design and development of the selected portable biogas digester from the previous design selection matrix method. For development, the materials and parts based on table 2 show the basic material for general type of portable biogas digester that were evaluated, such as the fixed dome, floating drum, and balloon biogas. Next, for development, a gas sensor measuring unit will be included to indicate the presence of collected biogas, where MQ2 sensor connected to the microcontroller Arduino Uno and serial LCD of I2C will be used. The development also included safety features to ensure the safety and monitor the internal pressure inside the gas storage tank, such as pressure gauge and safety valve. The third methodology is the determination of yield biogas for the developed portable biogas digester. First is to analyze the methane composition in the biogas sample using the gas chromatography method. Second is to determine the daily biogas requirement to meet the domestic biogas demand. Next, moving to the result and discussion. Based on the design selection matrix method, the portable fixed dome biogas digester was selected to be designed and fabricated as it has the highest score from the selection criteria for biogas digester for domestic use. Figure 10 shows the final development of the selected portable fixed dome biogas digester. Figure 11 shows the main part of the developed portable fixed dome biogas digester that has the gas storage tank connected to the digester tank consists of the stirrer, feedstock inlet, and slurry outlet. The total fabrication cost was Rm 382 ringgit. To check the safety design of the developed portable fixed dome biogas digester, a simulated static pressure of 0.1 MPa was applied to the gas storage tank. Figure 12 shows the simulated pressure of 2.675 MPa acting inside the gas storage. According to the thin wall pressure vessel theory, ratio of radius to wall thickness greater than 10 able to resist internal pressure with condition that internal pressure greater than external pressure. According to the developed portable fixed dome biogas digester, it has the ratio of radius to wall thickness of 37, which greater than 10, thus it able to resist the internal pressure. To further ensure the safety, 3-bar pressure relief valve is installed to ensure that pressure inside the biogas storage tank does not increase up to a level that could risk the gas storage tank to break. Figure 13 shows the size and dimension of the developed portable fixed dome biogas digester with working volume of 80% from the 1.5 m3 estimated volume. It has two operational ways with and without the digester tank. Figure 14 shows the PVC stirrer and feedstock inlet, which required for mixing of substrate, and the feedstock inlet is designed to be straight down to the base to prevent gas from entering and escaping the system during feeding operation. To further ensure safety, PVC class EAB4949 was used to improve the durability of the stirrer. Table 3 shows the gas chromatography result for each collected biogas sample. According to sample 5, it has methane composition of 60.37%. This is due to additional cow dung added on day 55 with proper mixing and sufficient hydraulic retention time of 25 days. There is significant difference in methane composition between sample 1 and the standard biogas study by Gakwat and Kati in 2014. This is due to constraint on time of mixing and insufficient of feedstock. Supported by House in 2010, stated that yield biogas will increase for a period of time until it reaches a maximum and begin to slowly decrease according to the anaerobic digestion parameter. From the obtained value of volume of digester, daily substrate input, total volatile solid and biogas yield factor, the daily volume of biogas was determined to be 0.614 m3 per day. Therefore, at 80% of working volume, the developed digester was estimated to be able to cover the daily cooking gas requirement for a household of 5 people by consuming 4 days of its daily biogas production at 60.37 combustible methane gas composition. Conclusion: the developed portable fixed dome biogas digester meet with the domestic consideration on durability of parts material, accessibility, and cost effectivity. In terms of biogas production for domestic use, the developed digester able to cover the daily cooking gas requirement, which can further enhance with sufficient feedstock supply and proper mixing of substrate. Finally, the impact of the developed portable fixed dome biogas digester. First, towards society is the application of portable biogas digester in domestic area help to contribute in managing and reducing the domestic waste, such as reducing the uncontrolled food waste disposal that might cause developing bad odor and increasing rodent population. Next, the impact towards safety is the developed portable fixed dome biogas digester installed with safety valve to prevent from high internal pressure inside the gas storage tank that could lead to explosion. Finally, the health impact, the developed portable fixed dome biogas digester taking consideration on the ergonomic factor. The height of the stirrer was set to height level of arm of an adult user. Thus, the user does not have to bend to turn the stirrer handle.